So let's come back and start working with exponential equations. And remember, we've used this property before. As long as you have a positive base that isn't 1, if you plug in u and v and get out the same thing, then you must have plugged in the same thing. It's a one-to-one function. So let's use that to try to find a value of x for which 3 to the x is equal to 7, or 5 times 4 to the x is equal to 3. Your final result might involve some logarithms, and you might have to do a calculator approximation, although you don't have to. An exact answer involving logarithms is fine. But try to do these, and then come back. So hopefully we tried these. So let's take a look at the first. 7 can't be an integer power of 3, so I'm not going to be able to do this using the same tricks we've used before. 3 to the first is too small, 3 squared is too big. So what we have to do is convert it into a logarithmic expression. X is log base 3 of 7. That's just converting the exponential into a logarithm. Now, if we wanted to approximate this, by the way, if this was an exam, I would accept this as a completely accurate, fully correct answer. X is log base 3 of 7. That is exactly correct. If you want to estimate it, you can change a base into natural or common logs, which would then, you could get like some approximation, 1 point something or other. Okay, another way you could do this problem, you can take the natural logarithm of both sides, or the common log, but usually we take the natural log. So if I start off with the x equals 7 and take a natural log of both sides, great, there we are. And now use the power property of logarithms to bring that x down, and then divide by log 3, and you get exactly the same thing. Okay, and this does, really strike us as a change of base formula that yes, this is exactly a log base 3 of 7, which is approximately 1.77. Remember, we knew the answer was going to be in between 1 and 2 because 3 to the first is too small and 3 squared is too big. So we knew the answer was going to be in between 1 and 2. And just a simple check like that, by the way. Oh, 3 to the x equals 7. 1 is too small, 2 is too big. Great. Now if you accidentally punch something into your calculator wrong and it tells you the answer is 312, you're like, no, it wasn't. I made an error. Okay, so knowing how to do this stuff by hand really can save you pain in making simple avoidable mistakes due to lost negative signs, accidentally writing 1 plus 7 as 17, stuff like that. Okay, so this other one was 5 times 4 to the x equals 3. It's very similar, except you can't just start by converting into a logarithmic expression. We need to start by dividing by 5. Now I can convert it into a log. X is the log base 4 of 3/5. As an exact answer, you're done. But if you wanted to change base to base e, you could write it like this. You could also, by the way, write this numerator as log 3 minus 5 over log 4. If you were back, in the pre-electronic calculator era and you just had a table of values, you would even then convert log 4 as the log of 2 squared, which you would then replace as 2 times the natural log of 2. So you would look up these specific values and then you would compute the result. But any of these would be fine. Okay? We're just getting used to manipulating them right now. Okay, so can you solve this? So pause here, try to solve for x. Okay, hopefully we gave it a shot. I can't go directly to a logarithmic form because there's exponential expressions on both sides. Okay, and you can't express 7 as a power of 2 or vice versa. So what you should do is begin by taking a log of both sides. If I take the natural log of both sides, we just end up with the log of 7 to the x minus 3 equals the log of 2 to the 2x plus 1. And then we're going to use that power property, bring down the powers as factors. These parentheses are very, very helpful. A lot of students, by the way, would write this. And then in the next step, they'd forget that this log 7 was supposed to distribute across the entire term. So use parentheses, avoid mistakes. If I distribute that out, we have a couple of terms that involve an x and a couple of terms don't. So let's get all the x's to one side and all the non-x's to the other. Okay, so we've moved this 2 log 2x over here, and we've moved this 3 log 7 over there by adding them and subtracting them respectively. So now I have an x that I can factor out, and then I can divide out that factor of log 7 minus 2 log 2. There's your answer. What's the solution x? Well, it's 3 times log 7 plus log 2 over log 7 minus 2 log 2. which a calculator will tell you is about 11.670. Okay, and as I've said a couple times now, if to this point, as far as I'm concerned, you're done. I really don't care if you know how to use your calculator. This is a math class. It is not a use your calculator class. We let you use calculators, but they are never, never, and I want to stress this very much, never required, except for a couple homework problems that involve some like big charts of data. But exam problems, you are never required to use a calculator. Okay, how about this one? So this one poses some new challenges. Now, rather than just jump right to the solution, so what might you try? You might say, well, gosh, in the previous problem, we had something like this. If I just take these terms and I move them over, I might call this 12 minus 3 to the x. And now I might try to take the log of both sides, but we very quickly run into a problem. The left-hand side is just x times 9. But the right-hand side, there's nothing I can do with because of this minus sign in here. So the previous technique won't really work. This is a trick type problem. There's a little trick to it, which is to notice that 9 is 3 squared. So if I replace 9 with 3 squared, I can use properties of exponents and call it 3 to the 2x, which happens to also be equal to 3 to the x squared. Instead of calling this 3 squared to the x, we've called it 3 to the x squared. So we can rewrite our original expression as 3 to the x squared plus 3 to the x minus 12 is 0. Now if I then take the 3 to the x and I rename it as something else, let's just call it u. Then we have u squared plus u minus 12 equals 0, which factors. This is off on the right. U minus 3 times u plus 4 is 0. But remember, u was 3 to the x. Now I have a nice factor. So u could equal 3, or u could equal 4, meaning 3 to the x could equal 3, or 3 to the x could equal minus 4. And now these can be solved normally. Okay. So 3 to the x equals 3 is solved by x equals 1. 3 to the first is 3, but notice 3 to the any power is never negative, so this has no solutions. This has the solution x equals 1. So that's the only solution. Okay, how about this? Now we really have to use a graphing utility. There is a technique to do this by hand. It's very uncommon. Most people never learn it. I have heard of it. I think it's called the Lambert W function. So just like logarithms is like what we invented so that we could solve certain exponentials, the Lambert W function was invented to solve things kind of like this, but I don't even really know how to use it. Once you get to stuff that mixes exponentials with just normal powers like x, you really have to rely on technology to solve it. So really all we can do is graph x plus e to the x and y equals 3 and find where they intersect using a calculator, and the estimate is about 0.792. And honestly, that's the only thing you could have done here. Okay, so if you are mixing exponents with normal powers of x, or you're mixing logarithms with normal powers of x, or exponents with logarithms, it gets to be a real mess and you need technology. But if you just have expressions involving only logarithms of the same base or only exponential things, then you can use the sort of techniques we learned in this section.